we're going to skip example 1, so let's go to example 2. Bacteria in a lab culture grows in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. Okay, when it says directly proportional, that means that you can multiply a constant like k times whatever it's talking about. Okay, so when it says instantaneous rate of change, we're talking about the derivative. So in this case, we're going to say that the derivative of the bacteria related to time is directly proportional to bacteria. That's all A is asking. When it says write a differential equation, that's all it's asking. So B says solve it. And this is what you've been doing, where you get the B's together and the T's together. And I wrote them with B's and T's so that it represents like the problem. So if I cross multiply, remember this is like over 1, so that would be dB equals KB dt. I really just need to divide by the B, so I would get dB over B equals K dt. Find the antiderivative. So that would be natural log of B equals KT plus C, because T is the variable. Alright, solve for B. Since B is the thing on top, we're going to solve for B. Remember there's an understood E right there, so that would be B equals E to the KT plus C. Don't forget to make our little constant there. If you want to call it little b, or if you want to call it something different, that's okay. So big B equals little b e to the KT. Alright, C. Suppose that initially there are 5 million bacteria. So initially there's 5 million bacteria. That's telling you when the time is 0 that there's 5 million. And we're just going to keep in mind that bacteria is a million. 3 hours later, the number has grown to 7 million. Write the particular equation that expresses the number of billions as a function of hours. So we're going to use the 0, 5 and the 3, 7 to find everything we need in the equation that we just solved. We're going to start with the 0 and the 5. And you're going to plug that in for the B and the T. So 5 equals little b e to the k times 0. Alright, k times 0 is 0, e to the 0 is 1, so that means little b is 5. So then we're going to plug in the 3 and the 7. 7 equals, plug in your 5 you just found, e to the k times 3. Now we're trying to find k. So first thing you want to do is you want to divide 7 and 5. So you get 1.4 equals e to the 3k, or k times 3. Now, to get the k to come down, you're going to take the natural log on both sides. So I'm going to put a natural log here, and I'm going to put a natural log here. Now when you put a natural log in front of something that has a power, the rule is that the power can come down in front of the natural log. So we have natural log of 1.4 equals, bring down the 3k, natural log of e. Now, natural log of e is 1, so I can cross it out, or if you want to divide by natural log of e because you're not sure about that, then that's fine. So now I want to find natural log of 1.4, and then I want to divide by 3, and I get 0.112. Now keep that whole k in the calculator because we're going to use it when we solve the rest of the problem. And so our final equation here is big B equals 5e to the 0.112 t. All right, E. What will the bacteria population be 1 full day after the measurement? Since T is in hours, since we did and see how it was 3 hours later, then on E we're just going to let T equals 24, and you just plug in 24 to find the bacteria. You get 73.789 million. All right, F. When will the population reach 1 billion? So this time the B is 1, so we would have 1 billion, which since B is in millions, that really means 1,000 millions. So we set that equal to 5e to the 0.112t, and we're looking for the time. So to solve that, you divide 1,005. Take the natural log on both sides again, just like we did earlier. Remember, that's 1. And you're going to do natural log of 200 divided by that number that you're going to keep in the calculator. And you're going to get 47.240 hours. Alright, here's example 3. And basically it's the same kind of problem as the other one. It just is written differently. We're going to be dealing with Newton's law of cooling whenever we practice this in class, cooling and heating. And so this is what the problem's talking about. And you kind of need to know this a little bit, or at least understand the equation. So Newton's law of cooling and heating says that the temperature of an object decreases or increases at a rate proportional to the difference between the temperature and its surroundings. And so the actual situation that we have here is that the normal body temperature is 37 degrees Celsius. A person was found dead whose temperature was 35 degrees Celsius in a room with temperature of 20 degrees Celsius. 2 hours later, the temperature of the body was 25 degrees Celsius. How long was the person dead before he was found? Alright, I'm going to skip and do this on a separate slide because there's not enough room here for me to do the information. I do want to tell you that this first part of the information, though, is an actual equation. So before we get to the actual numbers, the Newton's law of cooling and heating says that the temperature, with respect to time, the rate of change of the temperature is proportional to, so K times, the difference, that means I'm going to subtract something, between its temperature and the temperature of the surroundings. So that would be the temperature and the room temperature. So that part right there, the dt over dt equals k t minus r. That's a pretty important equation that you just need to know. Okay? Alright, so here's that equation that we just said. And I'm going to go ahead and fill in the 20 because the problem tells you that the room temperature in that problem is 20 degrees. Now, the other information that the problem tells you, it tells you the normal body temperature, which is 37 degrees. Maybe we'll do something with that later. So 37, I'm just going to put out, oops, that's not right. 37, we're going to have time and we're going to have temperature. We're going to put 37 here, and we're just going to remember that that's the normal body temperature. It tells you that the person was found dead whose temperature was 35 degrees. So when the person was found, that's the initial time, and that's 35 degrees. And then 2 hours later, the temperature was 25. So that's more information that we know. So it's kind of like the last problem, except that doesn't give you the ABCD parts. But the first thing you're going to do is you're going to solve the original equation that we have here. So we're going to get the big T's together, cross multiply, and the little t's together if there are any. So I want to divide by the t minus 20. Then I'm going to take the antiderivative on both sides. That will give me natural log of t minus 20 equals kt, don't forget your plus c. Rewrite it, don't forget your e right there, t minus 20 equals e to that power, so e to the kt plus c. I'll go ahead and put that b in there because we know that that's important. And then we're going to add 20. So there's the first part of the equation. That's sort of the temperature equation. And now after we find the temperature equation, now we're going to use the other information that we have in our table. Start with the 35 and the 0. And now we're going to solve for b. So subtract 20. E to the 0 is 1, so we know that b is 15. And we're going to rewrite the equation again, and we're going to use the 25 and the 2. Subtract 20. Divide by 15. Take the natural log on both sides. And you get negative 0.549. Keep that whole thing in the calculator. You'll need it. So now we have the equation t equals 15e to the negative 0.549 t plus 20. Now the question says, how long was the person dead before he was found? So that 37 that they gave us in the original part of the problem, the normal body temperature is 37, what we're going to do is we're going to plug the 37 in for the temperature, because we're going to find out how long ago it was that the temperature was 37. Because when the temperature was last 37 is when the person died. So we have 37 equals 15e to the negative 0.549 t plus 20. And now we're just going to solve for t. Subtract 20. Divide by 15. Take the natural log on both sides. And then divide by that number that still is in your calculator. And I get negative 0.227, and so that means 0.227 hours before it was found. That's why it's negative, because it's before the time actually began. Okay, so here's the last example. And basically it's the same kind of problem. Let P of t represent the number of students in a school who buy their school lunch after t weeks. So we've got a P and a T. It is increasing at a rate proportionally to that, so that means it's going to be K times that, where the constant of proportionality is K. A says write a differential equation, so we know that the rate, which is the derivative, is equal to K times 600 minus P, because that's what it's proportional to. Alright, B says if 300 students buy their lunch initially and 400 buy their lunches after 10 weeks, solve the differential equation. Okay, so basically they're telling you that we have, originally after the first week, we have 300 students buying it, and then after 10 weeks we have 400 students buying it. We're going to use that information, but before we can do that, we have to solve the equation. So I'm going to go back to the other slide and try to solve it for you. So we already have this equation. Take a minute and see if you can get P by itself. So pause the video and see if you can get P by itself. What I'm going to do is I'm going to cross multiply. Divide by, actually, you know what I'm going to do? I'm going to factor out a -1 because I know that as long as it's a P, it'll make it easier. So I'm going to make it -K and then P, take out the -1 on each of them, P minus 600. And then I'm going to divide by P minus 600. You don't have to do that, but I think it makes it a little bit easier. Right, take the antiderivative. And you know what? That T wasn't there yet. But now it is because I'm taking the antiderivative. The E is there, so we've got P minus 600 equals E to that power. That's the same as B e to the negative KT. And then add 600. Alright, now we're going to use this equation to answer the question that it asked you. It gave you the 0, 300 and the 10, 400. So start off by plugging in the 0 and the 300, and then the 10 and the 400. So I'm going to leave the problem at this point, and I'm going to let you try to solve it, which means I want you to finish the B part, and I also want you to finish the C part. The C part says how many students will buy their lunches after 20 weeks. The C part's really easy. As long as you get B correct, then you're plugging in 20 for the weeks, and you'll just look for P. So in B, you'll plug in the 0, 300 first, and then that will help you figure out what the little b is. And then you'll plug in the 10 and the 400, and that will help you figure out what K is. And then you can solve for C.